Hello everyone, my name is Liu Ye from Nanyang Technological University, Singapore. Today I will present our work on automatic verification of smart contract fairness. This is a collaboration work with Shang-Wei and Rong Zhao from Ethereum. Smart contracts are computer programs running on blockchain platforms such as Ethereum and EOS. Specifically, users can interact with smart contracts by sending transactions. The execution results of transactions will be stored in the blockchain and remain immutable, which makes smart contracts suitable for trustless scenarios across multiple users. Smart contracts are used to power decentralized applications such as voting and auction, providing trustworthy services in a trustless environment. Recent research mainly focuses on the security aspects of smart contracts. There are many real-world attacks on smart contracts that may cause huge loss. For example, the Zhao re-entries attack caused a loss of $60 million. Apart from the security problems, the fairness problem of these smart contracts also pose real threats. Here are a lot of fairness issues related to smart contracts. The most infamous one is a Ponzi scheme. A Ponzi scheme is a form of fraud that lures investors and pays to the earliest investor with funds from more recent investors. The Ponzi schemes have been widely observed on Ethereum smart contracts. Moreover, collusion in smart contracts also poses threats to smart contracts fairness. Many believe smart contracts can be used to prevent crime, especially government corruption. However, these use cases may have fairness issues. For example, public procurement auction and electronic voting are very vulnerable to collusion. I will demonstrate some fairness issues of smart contracts with a motivation example. Then I will describe the framework of fairness verification and present our evaluation results on real-world smart contracts. Here is a real-world auction contract, CryptoRome auction. It implements an open auction. The highest bidder wins the auction, and latecomers can win if they bid $1 more than the highest bidder. Given three bidders A, B, C, they have different valuation on the auction item before the start of bidding. Bidding ends after a certain time period, and someone wins auction and pays the winning price. Now, user A bid $3. To do that, the user first calls the bid function. Then the condition rule inside function will be checked. Since the condition rule failed, so the last statement will be executed. In the end, the contract updates the highest bidder to user A has bid to $3. Similarly, user B and user C can bid and update the variable highest bidder and highest bid accordingly. User B bids $4 to the auction, and user C bids $6. Finally, user C wins auction and pays $6 as the auction clear price. However, user C can pay less money to win the auction. When user C is untruthful, C can bid less than his valuation on the auction. User C wins the auction and only pays $5. Moreover, the worst case is that user C colludes with user B. Now user B bids $0. User C bids $4. Finally, user C wins the auction but pay much less at $4. Apparently, these behaviors are not fair for user A who acts honestly. The verification on the fairness properties can be illustrated by the figure. We have 4 fairness properties. The definitions are detailed in the paper. Here we focus on checking collusion among 2 players for simplicity. Specifically, given a smart contract, our goal is to develop an automatic check to verify smart contract fairness properties. The verification result either indicates the smart contract is unfair through some counterexamples, or fair use bounded property checking or unbounded verification. I will show how we achieve the goal. This is our fast verification framework. We call it FairCon. There are three main stages: model construction, property checking, and fairness proof. FairCon tests the smart contract code, fetch property to be checked, and environment templates as input. We use symbolic execution technique and bounded property checking to try to find some counterexamples. We also explore the loop environments to prove the fetch properties if there are no counterexamples in our checking. At the first stage, we have a smart contract. Given fetch property, we instrument key players environment into the smart contract. We get harness program. Then we use symbolic execution to execute the harness program. The symbolic passes will be synchronized and to construct the boundary model through SMT encoding. The reason why we use the key players environment is that many unfair smart contracts can be reviewed using a small number of players. At this stage, we perform property checking on the boundary model. We will check specific fetch properties. If we found counterexamples, the contract is unfair. Otherwise, there will be some positive examples to help us prove the fetch property. At the last stage, we use environment techniques to prove the fetch property. Among the predefined templates, we can identify the environment candidates from the positive examples. We use definitely to verify if this environment candidate hold. If environment exists, we can check the conditions of fetch property and then prove it. Once proved, the contract is fair. Otherwise, the fetch remains unknown. In the next slides, I will show our implementation of the framework. A mechanism is a set of decision rules that generate outcome. Smart contract also define a set of rules inside function to decide what users can get. We can easily map smart contracts into mechanisms. Given a mechanism, user will be required to take some action as input. The mechanism will generate output based on the input. As for the outcome, there exists an allocation function to show who is the winner, and a transfer function to calculate how much the user pay. Usually, only the winner should pay the money. We can identify mechanism components in smart contracts. We take the messenger as an individual, and the messenger value is the price of auction. We also take the highest bidder as allocation and the highest bid as the auction clear price. And the outcome rule is a big function. Let's see how to analyze the mechanism model of smart contracts. Here is a three-player mechanism model of smart contract. In the model, there are three bidders, messenger 1, 2, 3, and different bid prices, messenger value 1, 2, 3. We use a zoom keyword to represent condition rule in the bid function. The rule is the latecomers bid price is $1 more than the previous one. The model also shows the allocation is awarded to the bidder with the highest bid price, and the payment is the highest bid price. Based on the mechanism model, we can check our fetch properties. Take truthfulness properties as an example. We have two different bid price settings. In the first setting, all bidders are truthful since the bid prices are equal to the valuations. In the second setting, only the third bidder is untruthful. We get a truthful formula used SMT encoding. Briefly, this is an assertion. that the difference between valuation and price of truthful setting must be no less than that of untruthful setting. We can use any SMT solver to check this formula. We find counterexamples so that truthfulness doesn't hold for this contract. Further, if the properties of smart contracts is proven, we should work on unbounded mechanism models. We use loop invariants to direct the French property proof on unbounded models. We have three invariant templates, one for allocation function, the other two are for price function. Top bidder means the winner is the bidder with the highest bid price. First price means the winner should pay the highest bid price. Second price means the winner should pay the second highest bid price. We use defining to verify the invariance candidates on smart contracts. If invariance exists, we can prove the French property straightforward. In some cases, invariants are missing, so the contract fairness is unknown. We evaluate our framework, FairCon, on 12 real-world auction smart contracts. The basic setting is free players mechanism model. We found there are 8 contracts do not meet any of our French properties, and 4 contracts meet some French properties. Moreover, the time used in property checking is very small, around 0.1 second for these free players mechanism models. To study the efficiency of property checking, we spend our evaluation on mechanism models of more than 3 players. We increase the bidders number from 3 to 8. We found the property checking time increased 90. Generally, checking time is less than 1 second. This indicates our property checking is efficient. We also observed the time used to extract the mechanism model. We found the extraction time increased nearly exponentially. Therefore, fast checking does not work for a large number of players, which requires us to use loop invariance techniques to prove fast property. This is our evaluation to prove fast properties of four contracts that meet some properties. For free contracts, we found the invariance and proved the French properties. Due to the lack of invariance, one contract is unknown regarding the French property. In the future, users can provide other feasible invariant templates to enhance the provability of FairCon. To conclude, in this work, we aim to automatically verify the French property of smart contracts. There are 4 French properties related to mechanism theory. We use bounded property checking to try to find counterexamples against French property, and loop invariant to prove French property. And our work can be extended by introducing more invariant templates of French property. That's all. Thank you.